Welcome back. This is the third video. It's also the final video for the probability density. I realized once I recorded, in some cases I misspoke. Sometimes I called probability instead of probability density. To be more clear, the rho itself is a probability density. And last time I left some homework for you guys to do. For instance, calculate expectation value of x. And when you plug it in, of course, the correct answer should be a. If you have x squared, there should be a squared. So it should be a squared. I hope you got the correct answer. Now, a little harder ones is this rho. The correct answer, this rho, probability density for the constant motion is 1 over L. L is the length of the road. You remember the length of a road. So let me show you. So this is the length of the road. So from here, the car travels in this direction. So this is from here all the way to that. The total length is L. And then probability density for this constant probability density is just 1 over L. And I hope you figured it out how this is calculated. Of course, these all entire materials as in our book. From that, you can also calculate the expectation value of x, just similar like what you do here, and also calculate x squared. You will be very surprised. You actually can compare with the results of the product in the box. The difference just by very little. So this is something I found myself is we are very proud of this particular results. It turns out if you just use a classical particle, you actually can calculate the exact same thing with the position operator, expectation value, and x squared. So they are almost identical to each other. They only differ by a very small amount. Finally, I would like to discuss why we called probability density. So the question is, can we call probability alone, just call it probability? The answer is no. The reason was that probability has no spatial dependence. So there's no spatial information. For instance, if I ask you, what's the probability that one particular electron will appear in the space? You could say 50%. Then you would ask where that is. Well, then you need the density itself. Now, in the solid-state physics later chapters, when we talk about probability density, we sometimes just call it density instead of call it probability, because you have very good statistics. So therefore, it doesn't matter. Suppose if you have a metal, you have so many electrons, so you just have the density itself should be good enough. But to be more formal, we need called probability density. So this is the conceptual, very important concept. It doesn't matter whether you are in the classical system that we just showed an example or in quantum system. The idea are exactly the same. And then some students do ask us, can we use the density alone without using the probability? Just call it density. Well, if you have many electrons, and so that's fine. You can definitely use the density, but there's one problem. What happens if you have a single particle? Then the density alone has no significance. The reason was that suppose I have one single electron shining through the slit, and I want to ask you to predict what the results behind of this. So this is not quantum mechanics can predict. So I'm going to write this down. Quantum mechanics does not predict where a particle lands. In other words, it does not tell you this single electron is going to land. It's going to land over here, over there, over here. It does not tell you this. This is the beyond quantum mechanics. In other words, you cannot ask this question to ask quantum mechanics, hey, please predict where this electron is going to be land on the screen. You cannot predict this. This is beyond quantum mechanics. Because as soon as you decided this electron is going to land over here, they will run into a theoretical problem immediately. So that's why this particular part is very crucial, because if you have one single electron or single particle, then the where it lands, it does not predict by the quantum mechanics. Quantum mechanics only predict most likely you're going to pi up here, less likely pi up there. So that is the probability density. That's also why in quantum mechanics we commonly called statistics. And this statistics has nothing to do with classical statistics. This statistics just allows us to reveal the wave nature of the particle. In other words, if I have a single electron, you basically probably just go and dot on the screen. But there's no wave, so to speak, even though the wave nature is there. But in order to reveal its wave nature, you need a statistics. So you're going to shine another electron, probably pine up over here, another electron, and pine up over there. So then gradually, the wave nature shows up. But that must be understood. The wave nature, even when the single electron is already there, it's just the wave nature cannot be shown up on experimentally. So experimentally, when you measure them, you want to see the wave nature. If you have a single electron, it cannot reveal that to you. You only have many electrons, or you need good statistics in order to reveal that's wave nature. And that is the probability density. That's why it's a lot harder. I put off this explanation to the very end. That's mainly because if you did not understand even the classical physics can use a probability, it's very difficult for you to understand the quantum mechanically, the probability density need additional idea, which is called statistics. So that's the statistics make the wave nature shows up. If you want to show the particle nature, you do not need statistics. You just open the slit real wide, and of course, sure enough, the electron is hit in the middle here, and never go anywhere else. That's the classical picture. It's also particle picture. But once you squeeze this, the slits a little bit narrower, comparable to double wavelengths of the of this electron. So in other words, D is comparable to W wavelengths. Then the wave nature shows up. The wave nature shows up only when you have good statistics. For instance, when we do electron diffraction, and you have to ramp up larger currents. If you have a smaller current, the interference pattern or diffraction pattern never shows up clearly. Just like single dot here, single dot there. But definitely there will be zero if this predicted to zero. There will be never shows up at this particular location. That's quantum can predict. So it can predict 100% without any uncertainty. Predict this is 0%. You will have chance to land over there. And here's percentage will be higher. So that's a quantum mechanics predict. And I hope you guys understand this idea. So I'm going to write a summary. The statistics, it depends on when you observe it. You need the statistics. Of course, wave nature is there already. See you next time. I hope you enjoyed my video. So that's the end of my third videos on the probability density. This is the hardest concept in quantum mechanics. I hope you enjoyed. Have a good day.